Can one of you confirm whether you can see my screen? It should be a web browser open something called Jupyter and PHY4024 for cosmology. Can you see it? Okay, so okay, right. So just need to confirm it. Right now, since I could not give you some of these course contents to you last time, so I have this document which I'm going to share with you, and just to give you an idea what kind of things that you are going to learn in this particular lecture series, right? Now the course unit is PHY4124 Astronomy and Cosmology. And the basic idea is the first 30 lectures that comes from PHY3232 is normally we count as the astronomy part, and then the second 30 lectures that you will be learning in the special degrees normally is what we count as cosmology. However, at this in this year, so I made this little change depending on the conditions that we have. So you have completed the 20 lectures, around 20 lectures from PHY3232, and then there are 10 lectures that remains. So I don't want you to wait until we start the general degree. Because of that, I made some changes in the course contents that is suitable for you, and start. So the last 40 lectures will be separated for you, right? Than the general degree students. And there is an advantage for you here as well, because you will be learning a bit more now for even for these last 10 lectures for the astronomy part, because that this will be important for you if somebody want to go for postgraduate studies, right? So I want to give you like a little bit more details in some of the things, not that much, but there will be slight changes. Now, in your course content, in the handbook that you have these topics mentioned under astronomy and cosmology. For the astronomy, it says energy production of in stars, and the stellar evolutionary processes where we stopped in PHY3232, and I will start from there. And apart from that, what you are going to learn here is energy production in stars is not a separate topic. You know that, right? So energy production means all these nuclear fusion reactions that goes with this stellar evolutionary process that we are learning. So these are combined together. And then the third topic is classification of stars and black holes. And under this, we will actually learn a little bit more about black holes separately. And then multiple star systems. This is about binary star systems. And also the stellar motion also we will learn about how stars move on the sky. Like there are different kinds of motions. And then star clusters. So the star clusters is the topic that we covered on the first day. This is about open star clusters and globular star clusters that we have learned. And then probably in the next week, we will learn about galaxies and their classifications. And then there is a separate topic called active galaxies. Maybe this will be combined with the other topics. And then the next level, that is groups, clusters, and superclusters of galaxies, right? Now, the reason that I want to cover these topics before the cosmology, you cannot actually separate like astronomy and cosmology when we go into like talk about the topics like galaxies and galaxy clusters, right? So once you talk about these, that is the point where you normally move into the second set of topics about cosmology, right? So we will cover these things. So my plan is to try to finish these topics up to the point 8 as soon as possible, probably within next week. And under this this topic about the black holes, I may take that into the cosmology part. So that depends, right? So I will briefly discuss with you about black holes initially, but we'll also talk about this part about the black holes as a separate chapter in cosmology at the beginning. This is because there are a lot of theories about general relativity which are involved when we talk about black holes. So it is very, very useful to talk it with the concepts that we have in general theory of relativity. Right. Now in the cosmology, these are the topics that are mentioned in your syllabus: issues in cosmology and cosmic distance scales. So that is how do you measure different distances when you go outside the galaxy, and then about the expansion of the universe and the Hubble law, age of the universe. These are, the idea is you should know a little bit about all these things by the end of this lecture series, and the gravitation and the general theory of relativity. Now, under general theory of relativity, we will actually go into a little bit more mathematics, which are about, like, talking about tensors, and then give some insight to you about, different mathematical concepts that you need to know when we talk about general theory of relativity, including Einstein's field equations, and then the principle of equivalence. All these things are, by the way, combined to each other, right? So even though they are like mentioned as topics, they will, like, connected to each other when you learn about those things. And then the geometry of the universe, that is whether we are living in an open universe, closed universe, or a flat universe, and then the cosmological principle, and then solutions to the Einstein equations, and the hot Big Bang, which is the theory about the formation of the universe, and then cosmic micro background radiation, matter in the universe, dark matter, dark energy, gamma ray bursts. We will learn about that today. And the inflationary universe, growth of large scale structure, and Planck era. Now, these topics are actually connected to each other. So this is, so I will not take one topic at each time and discuss about that. Instead of, you will learn about these things by the end of the lecture series, right? So that is the idea, because most of these things are connected to each other, which we need to talk together sometimes, right? So we will, for example, about dark matter, we will talk about dark matter probably in the we will start talking about dark matter in the next week when we talk about galaxies, right? Because there is a point where you need to talk about dark matter like that, and dark energy is a similar situation. And so I have mentioned here that apart from what we have learned about in the astronomy, there will be 10 extra lectures for astronomy, and rest will be inclined towards the cosmology. And I have mentioned it, we will not go through topic by topic. Instead, we will take, so I guess there are some mistakes here. Topic by topics, and right. Now, so I want to mention specifically about the general theory of relativity. So under the cosmology, we will actually spend a considerable amount of time the considerable amount of time to discuss these different concepts in general theory of relativity and the formulation of this theory, right? So this is about the mathematical, most of these things are related to mathematics, especially about the tensors. And so I guess there are some of you have done double maths, right? Is there anyone who has done like tensors?
So I was done.
Okay, so is that
Taranga.
so Taranga, right? Okay, you have done some tensors, Taranga, right? right? So maybe not clear, but I mean, for the others, I know that who are doing just maths and computer science, you may not have entered into these topics about the tensors. And because of that, I will try to go from the beginning. But anybody else who has like issues, maybe you can probably talk with those who actually have done double maths, like I guess Taranga and there are others I know that who did like 2 mathematics subjects. So they probably know a little bit better about tensors, but I will start from the as far as much as possible. I will try to go from the beginning, right? And right now for your exam, the final exam will be a 3-hour exam as usual, and the structure of the exam I will inform you a little bit later, right? So probably within next 2 or 3 weeks. Usually what we had was for this exam for the cosmology is a little bit different than the other exams. So what we had was we had 25 MCQs and 30 or 35 structured questions. So which makes it like 50 questions, right? So the 60 questions, which you have to, answer within like 1.5 hour, 1 hour and 45 minutes. And then there are 4 questions that you have to answer, which are like structured type questions, like essay type questions, sorry, right? So that is the composition of the exam paper for this cosmology, which we have followed up to now, but there may be a change at this time, which I'm still I have to talk about that. And so if how it will be changed, I will let you know. If it is going to change, I will let you know well ahead of time, right? Probably within the next 2 or 3 weeks. And so the first few days, these are the lectures that I am going to cover. So star clusters, depth of low mass stars, those 2 are already covered. And today I am going to talk about depth of high mass stars. And this actually includes supernovas, which will come as a result of, because some of the there are different types of supernovas. One type will come as a result of this depth of high mass stars. But we will talk about supernovas in general in this topic. And then about neutron stars and black holes very briefly. And then depth of low mass stars should not be here. I guess we have talked about that. Right. And now then we will talk about exoplanets as well. So this will be a very, very brief topic, which is about talking about how we detect planets in other solar systems, right? So this is one of the, so this was not in the previous set of lectures, but I have added it this time because this is one of the topics now used to be very popular among astronomy and maybe a little bit useful for you, anyone who wish to like follow like research in future. And because of that, I will very briefly talk about exoplanets, how they detect exoplanets and those things. And then stellar motion and binary stars. These are actually how stars move on the sky, different types of motions in different directions, and binary star systems. And perhaps actually exoplanets are somewhat close to this topic, so we'll talk about those two together. And then galaxies and galaxy clusters will be the final topic for the first 10 lectures. And then we will start about talking about cosmology. So that is about this second set of, topics that I have mentioned here, but they will be combined like together when we talk about those. And as references, You remember that I have given this book called OpenStax Astronomy book, right? So this was, so I have already given this even under the general degree. And this book is very, very useful for you. Try to read it. This, I mean, even without all these lectures, even if you read this particular book, you can get a very good idea, right? So I am not going to follow all the chapters in the book, but considerable amount of content that I have here has come from this particular book, and this is free to use. And if I have not mentioned before, the book is actually, you can download it as an app that you can have it in your phone, and it nicely give you a chapter by chapter reading even for your phone as well. So this is, I mean, mobile phone friendly one. So it will be very useful for you, right? And then there are two books that I have mentioned here. The first one is Most Incomprehensible Thing, Notes Towards Very Gentle Introduction to Mathematics of Relativity, which is the book that I used to get some of these mathematical introductions to the relativity, especially for the general relativity, assuming that you have done special theory of relativity before, right? And book contains both the general and special relativity. But this is a very useful book. Even if you read yourself, you can understand most of the things, right? The mathematics is very easy to follow. And then relativity, gravitation, and cosmology, which kind of inclined a little bit more higher mathematics, and also some of the applications in general theory of relativity, right? Now, apart from those, I just have another book, say, about gravity. So I will add that here as well. And these books are for your references. And I know that this first book is completely free. Second book, if you search in the internet, you probably should be able to find a PDF of that as well. Those are like very nice books for you to read. And right, so that's kind of an idea that I want to give you what we are covering under this series of lectures. Now let me go to the lecture today. That's about death of high mass stars. Right, so you should be able to see the presentation right now about death of high mass stars. Can one of you confirm me whether you can see the presentation or not? Okay, so I guess everyone else can see the presentation as well. Right. So if you remember that what we have talked last week was this branch right here. What happens to these low mass stars? So they will become red giant, and then we will have a planetary nebula. And at the same time, the final star will become a white dwarf, right? So this is where we stopped. And as you can see here, after a white dwarf, there are some other branches that you can see here. That is the type 1a supernova and the nova. And this part, we will also discuss this part under death of high mass stars when we talk about supernovas, right? Because there are two different types of supernovas that we are going to talk here. And one type is due to these high mass stars, and the other type is as a result of these low mass stars. So we will take those two together and discuss. Right. Now, if you look at these high mass stars compared to the low mass stars, for the low mass stars, we remember that last Monday we told that they have carbon in their cores, but they are not able to burn this carbon into heavy metals, right? Because their mass is lower, so they don't have enough, they don't create enough central temperature to burn carbon into those heavy elements, right? But this is not the case for these high mass stars. They have enough temperature at the center of the star to burn carbon into these heavy elements. For example, normally to burn carbon, you need a temperature around 600 million degrees Kelvin, as I have mentioned here. And these heavy stars can create that temperature at the center, right? Now, as a result of that, the carbon at the center will be burned into these additional heavy elements such as neon, oxygen, magnesium, and silicon. Right? So this goes on, but what happens is, normally what has happened to these stars was they have hydrogen at the center, and then they burn hydrogen into helium, and then helium into carbon, right? Remember that when this happens, at the center you have carbon, and then there are layers, helium, there is a shell of helium, and then hydrogen outside. And the similar thing will happen to these when you have these heavy elements on the star, you have carbon, and then carbon will be burned into these heavy elements such as neon, oxygen, magnesium. And what happens is, this will lead to an onion skin layer of materials in the core, right? So what this means is, if you kind of consider an onion, you have layers, layer by layer you can remove, right? So the same thing happens for these stars. The temperature will be increased with the depth in the star. When you go to the center of the star, the temperature will be higher, and each successive stage occurs faster than the last one. That means when you go for these heavy metals, the next heavier metal will create faster, right? So that's what happens. Now, at the end, what you will have is this type of structure. At the center, you have an iron core, and then you have silicon, oxygen, neon, carbon, helium, hydrogen. Right? So that's what normally happens. So when you go towards the center, you will have more and more heavier metals, because heavier metals are created at the central region. Central region is the place where you have the highest temperature. So once the temperature increases, the carbon will become a more heavy element, and then it will become another heavy element like that, right? But there is a limit for this one. That limit is iron, right? So iron is the final one. Anybody knows why it stops from the iron? I mean, if you have done like some nuclear physics in your secondary, you should understand why it stops at iron. Anybody can answer for that? Now, this is actually due to the fact that if you have learned about this binding curve, right, for nuclear, when you look at the nuclear reactions, there is a place where you go to the highest level and then come down, right? So this top level, you have the iron. So that is the heaviest element that you can create. And after that, you cannot create any element through nuclear fusion reactions, right? So that is the reason why it stops at iron, right? because you cannot, because it's unable to produce energy via fusion. So the iron is the heaviest element that you can produce, and then the fusion reaction stops, right? So that is not something specific to stars. So that comes from nuclear physics, right? So this is where you apply the knowledge of physics to astronomy, right? So make sure that you understand it. And what happens is that when all these fusion reactions stops at the end, at the center, when you have iron, then the gravity takes over, right? Remember that there are two forces that always compete inside these stars. That is the pressure created due to the temperature at the central part of the star and the gravitational force, right? Gravity. So those are the two forces that compete each other. When fusion reactions stops at the center, what happens is there is nothing to create that pressure at the central region. So then the gravity takes over. That means the gravity wins at that point. So the star continues to collapse after that, right? Because gravity is an attractive force and there is nothing to compete with that to stop that force, right? Now, a large mass and high temperature involves make this process more violent, and there is something special that happens at this particular point. So what happens is now you have a very high temperature at the central region and you have iron at the center, right? And this core temperature, which means at the central region of the temperature rises to nearly 10 million Kelvin. So it's a huge temperature. And under this temperature, what happens is this will create photons with extremely high energies, right? Remember, this is not protons, this is photons, right? Now, these photons can break up heavy elements in the core, right? So you have the core with this iron, which are very heavy elements, but these photons that creates at this higher temperature, close to 10 billion Kelvin, is capable of break up these heavy elements and leaving behind only protons, neutrons, and electrons, right? Now, this process is called photodisintegration, right? This is something very specific that happens at the center of these stars at the end, right? Once they stop all the nuclear like fusion reactions, the temperature goes up to very high value like 10 billion Kelvin at the center, and this will create these high energy photons, and these photons will break up these heavy elements such as iron in the core, and once they break up, what you will have is electron, protons, and neutrons, right? And this complete process is called photodisintegration, and this is what happens at the end at the central region, center of these heavy stars. Right. Now, so that's as a result of this particular process is where you have these supernovas, right? Now what happens is, now you have electrons, protons, and neutrons at the central region. And at the same time, this core collapse of 5 mass star continues because of the gravity, it continues to collapse. And so what happens is this leads to very high densities at the central region. And as a result of that, now you have electrons, protons, and neutrons at the center, and electrons and protons are squeezed together, right? And they will form neutrons, right? So this is what happens. Remember, initially you had iron at the center, and due to this process called photodisintegration, these heavy elements break up into electrons, protons, and neutrons. Now, after that, when star continues to collapse, the density of the central region will increase continuously, and as a result of that, the electrons and protons will squeeze together and will form neutrons, right? So at the end, you will only have neutrons in these heavy stars, right? Now this collapsing is suddenly stops when you have neutrons in contact with one another, right? Remember that you only have neutrons, and still this, because of the gravity, the star continues to collapse. And as a result of that, the neutrons will come into contact with one another. And at this particular point, it is very difficult to compress the matter further. And this is due to the fact that the neutrons create a pressure, and we call this as a neutron degenerate pressure. Right? And what happens at this point is, you have a very dense core at the central region. And because of this very dense core, the matter that like plunge inwards will rebound towards the outward direction at a very high speed, right? So just in your mind, just think about this situation. Now you have neutrons at the central region, and they are very densely packed, so that you have a very dense central region. But still, gravity is always an attractive force. Because of that, all these material in the outside of this core will plunging towards this dense core. And because of this very high dense core, all these materials that comes towards the central region will rebound to the outward direction, right? And this happens at very high speeds. And this phenomena is normally called as core bounce, right? And as a result of this rebounds of this material, this will generate a very powerful shock wave, right? And as a result of that, all the materials surrounding this core will be blasted away. And this particular process is a huge explosion. And this is called a core collapse supernova, right? And also this is also called as type 2 supernova, right? So I hope now today you will get the idea what these supernova explosions means, right? So you probably have heard this word everywhere. So once again, what happens is you have these heavy stars. So heavy stars burn materials and make heavy elements until the central region have iron. And once you have iron at the core, then the temperature rises for very huge values like 10 billion Kelvin. At this particular point, you have this process called photodisintegration, and under this photodisintegration, these heavy metals will be, they have heavy metals will become electrons, neutrons, and protons as a result of the photodisintegration. And then when the central region is further collapsed, then electrons and protons will be combined to become neutrons, and at the end you will have only neutrons. And still the gravitation, because of the gravitational force, the star is continuing to collapse. And as a result of that, all the neutrons available at the center will be packed very densely. And then all the materials that come towards the central region will be rebound because now neutrons are very densely packed, right? As a result of that, you have this thing called core bounce, and this rebouncing actually happens at very fast, high speeds. And as a result of that, this will generate very powerful shock waves, and because of that, all the surrounding materials around the core will be blasted away. Right? And this process is a huge explosion, and this is why we call that as a core collapse supernova. Right? So if somebody asks from you how supernova occurs, then you need to, I expect that you should be able to explain it in this way, right? And this is also called a type 2 supernovae, right? And so, by the way, supernova is the singular word, and supernovae is the plural. And right now, this is one type of supernova that can occur. And as you say that, as I mentioned, that this is a type 2 supernova, which means that there should be other types of supernovas, right? And in fact, there is another type of supernova that I'm going to talk is called type 1A supernova. And also there is another one called nova or novae, right, in plural word. Now that's what happens to these heavy stars. And for the white dwarfs, remember that the last time we talked about white dwarfs, so that is the endpoint of these low mass stars. Now, not all stellar explosions occur as a result of ultimate death of a high mass star. Right? White dwarfs are often the site of explosions through the process that is very different. So what I am talking here is this type 2 supernova occurs as a result of this process inside high mass stars. And white dwarfs that we talked last Monday happens, or we have white dwarfs as a result of this evolutionary process for low mass stars. Right? Normally, these isolated white dwarfs are very cool and fade because they will, they don't have reactions that going on. They will gradually become cool and fade. However, there are some situations that these white dwarfs has another close stellar companion. So that means another star, right? And if that happens, due to these gravitational forces, this white dwarf can accrete additional matter from this close by stellar companion, right? So this is something that can happen. And when enough matter build up on the surface of this white dwarf, if it is a normal star, a normal star mainly has hydrogen gas, right? So when matter is accreted towards the white dwarf, most of the time what you get is hydrogen gas. So when enough matter builds up on the surface of the white dwarf, what will happen is this hydrogen gas is what comes onto the white dwarf surface. The hydrogen gas will ignite and undergo a thermonuclear fusion. When matter accreted too much, when the correct temperature comes on, the hydrogen can undergo this thermonuclear fusion, right? So we talked about this under low mass stars as well. And as a result of this, once you have a thermonuclear fusion on the surface, this will cause this white dwarf to brighten dramatically for a few days and then fading back to normal. Once you have this hydrogen fusion reactions, the surface of the white dwarfs will become very bright, right? And this particular process is what we called as a nova, right? In plural, we used to tell that novae, right? If there are several novas, right? And this is another one that, that we have to discuss. And remember that we talked about type 2 supernova. Now this is just we call nova or novae in plural. And this is as a result of white dwarf accreting hydrogen from a companion, stellar companion, right? And here is an artistic image that shows you how this white dwarf can become a nova, right? So you have this white dwarf right here, and then there is a normal star, and then the white dwarf accretes matter from this normal star, and they goes around the white dwarf, making an accretion disk. And this, once enough hydrogen matter is collected here, they will go to that thermonuclear fusion, and as a result of that, this will get very bright at some point, right? So this is how we will have a nova at the end. And here is an example for a nova that has happened, called Nova Hercules in 1934, March 19. So these are like different times that it took. Here is how it looks like when it was, shining up with this all the material collected from the stellar companion in 1934. And once it got faded away, the same star looks like this in 1935, right? So I hope now it should be clear for you and this is called Nova Hercules. And there is actually Nova that kind of going on in these days as well. And I can't remember the name of that. I was checking this whether we can observe it, but unfortunately this is below the horizon for us most of the time. So I have no point of like looking at it from here. Right. Now that is, so we talked about type 2 supernova and nova. And then there is another type called carbon detonation supernova or type 1A supernova. Right. Now, as the name suggests, you should be thinking that maybe there are another types of supernovas. Right? And yes, there is something called type 1C supernova. That's a different, bit different process. And then there are type something called kilonova as well. So these are like things that are there, but for the time being, I will discuss about these three types of supernovas. Now, the same process for the nova. Remember that for the nova, you have a white dwarf, and then there is a companion star that could accrete that will give matter to this white dwarf. Right now, there are situations if the mass of the white dwarf exceeds 1.4 solar masses, and by the way, this should be like here, it should be solar mass, right? For some reason, the notation is not there. That is called solar masses. And this can no longer supported by electron pressure, right? Now, when this matter accreted from a companion star, and if the mass of the white dwarf exceeds this particular limit, 1.4 solar mass, it can no longer supported by the electron pressure. Now remember that how the white dwarf is balanced, right? Last Monday we talked about this. The white dwarf is balanced under electron degenerate pressure, right? Because electron creates a pressure at the center, and that is how white dwarf is balanced. But when more material is accreted from this surrounding surrounding or close by star, and if the white dwarf exceeds this limit of mass 1.4 solar mass, then this electron pressure cannot support, right, to balance the white dwarf. I mean, if this limit does not exceed, then it is fine, it will become a nova, right, as we discussed in the previous slide. But if enough material is accreted, and if this limit 1.4 solar mass exceeds, then what happens is the white dwarf will begin to collapse, right? And this leads to very high temperature, which causes the ignition of the carbon throughout the entire white dwarf. You know that at the center you have carbon, right? So that's how they became white dwarf, because they didn't have enough temperature to burn carbon at that point. However, when you have enough material, and if the mass of the white dwarf exceed this particular limit, 1.4 solar mass, what happens is the entire white dwarf, there will be an ignition of carbon throughout the entire white dwarf, and the white dwarf completely explodes as a result of that. Right? And this process is called a carbon detonation supernova or a type 1A supernova. Right? So both names refer to the same thing. Right? Now, remember that now, once again, if I summarize this, we have talked about three different types of supernovas. Right? One thing is type 2 supernova that happens for high mass stars when you have iron at the center and goes through this photo disintegration process, and then as a result of that, you have neutrons at the center, and once the matter plunging towards the center, the neutron degenerate pressure stops it, and as a result of that, those matter bounce back to the outward again, making shock waves, and then as a result of, and because of that, you will have all this material outside the core of the high mass star will be exploded and ejected, and that is called type 2 supernova. And then we talked about white dwarfs. When white dwarfs accrete some matters from a surrounding star, especially hydrogen, so the hydrogen will ignite and will become, from the fusion reactions, hydrogen will ignite. As a result of that, this white dwarf will be brightened up for some time and then will fade away. and that is called a nova, right? Now for this one, for the carbon detonation of type 1a supernova, it's the same process that we talk for the nova. However, if more material is collected around the white dwarf, and if this particular limit 1.4 solar mass is exceeded, then what will happen is there will be an ignition of carbon throughout the entire white dwarf star, and as a result of that, the star will completely explode, right? And this is called the carbon detonation supernova, right? So those are the three different things that we learn. So make sure that you understand the differences between those processes, right? And at the same time, this limit 1.4 solar mass has a specific name that is called Chandrasekhar mass or Chandrasekhar limit. And this is under the name of this famous Indian physicist who discovered this limit, right? So make sure that you understand these three processes separately. And this type 1a supernova is actually very important for us, and we will learn this in cosmology part as well when you talk about distance indicators. If the distances are far away from the galaxy, there should be a way. I mean, once if you can locate a type 1a supernova in one of these distance galaxies, you can actually very accurately measure the distance to that particular galaxy, right? And because of that, type 1a supernova is used as a very powerful method to measure the distances to galaxies that are very far away from us, right? And I'm not going to explain it here because we will talk about that separately, right? Now that's about up to now. What we have talked about is what happened to these high mass stars, and eventually, as a result of these nuclear reactions and different other processes, there is this process called supernova explosions that we talk. And now let's look at a little bit more into this about these supernova explosions, whether we can observe these supernova explosions, right? And as you can understand that these are like explosions of the stars, which means the supernovae event should be very bright, which gives off much light as hundreds of billions of stars, right? So they will give you enormous amount of energy, right? And when a supernova occurs in our galaxy, it may be visible with the naked eye, right? I mean, this is the practical situation. If you have a supernova explosion, everyone should be able to see it from the naked eye because of the huge amount of energy that is involved. Now, have anybody seen like a supernova before in our galaxy? I guess the answer should be no, right? So you have not seen the one, right? I mean, even though it can be seen from the naked eye. Now, the reason is these are rare, right? I mean, rare to observe. In the recorded history, there are only 6 supernovas that have been observed in the Milky Way, right? There are only 6. The first one was in AD 185. Which was bright enough to be seen during the daytime as well. So you can see how bright it was. And then there is the second one, the Tramp supernova occurred in 1054. This is a long time ago. And its appearance, this was actually recorded by some of the Chinese and Middle Eastern astronomers and the people in North America as well. Now, the most recent supernova that is observed by Johannes Kepler happened 1604, right? Now, the question that you should have is, then are these supernovas are rare, right? Now, on average, a supernova explosion occurs somewhere in the Milky Way galaxy every 25 to 100 years, right? So this is our estimation somehow. There may be one for every 25 to 100 years, so seems to be rare, right? Now, it is very interesting to see that, we talked about these telescopes at the beginning of this course, that after the invention of the telescope, no supernova explosions has been observable in our galaxy, right? So after we invented the telescope, we have not observed any kind of supernova. Right? So it's a long, I mean, it's almost, I guess, more than 400 years in our galaxy, right? Either we have been exceptionally unlucky, or more likely recent explosions have taken place in parts of the galaxies where interstellar dust block the light from reaching us. And you know that there is this interstellar dust in our galaxy, and we cannot observe everything inside our galaxy, right? Because we are within the galaxy, right? There are certain regions that we cannot see anything in our galaxy. So even though there should be one supernova for every 25 to 100 years, it may have happened in a place where we cannot see it, right? So that may be the reason. And since the explosion of visible supernova is a chance event, there is no way to say when the next one might occur. So the thing is, you cannot predict those, right? Otherwise, you can predict. No, you cannot predict that this will happen. I mean, this next one will happen in this place or something like that. And we do not have that much of technology, and I mean, there is no way of doing that. And the thing is, if you have seen a supernova for the first time, and you will be famous, right? Now that was about our own galaxy, but actually there are supernovas that have observed in other galaxies. And in 1987, astronomers in Chile, so Chile is in a city in South America, by the way. So they have witnessed a supernova in Large Magellanic Cloud, right? Large Magellanic Cloud is a small galaxy, in fact, a dwarf galaxy. We will learn about these galaxies in next week, I guess. So these astronomers have observed a supernova in this particular galaxy, Large Magellanic Cloud, in 1987. And this was named as SN 1987A, with the name that was observed. And this was the nearest and brightest supernova seen in modern times, which was easily visible to the naked eye as well. And there are some other more information that I have mentioned here, what kind of star that led to this supergiant and all these things. And astronomers actually monitoring the remnant of the supernova ever since, which means the remainings after the supernova explosion. And this is a Hubble Space Telescope image of the supernova 1987A, which was taken later. So this is the supernova remnant actually. So I have some information there as well, which I'm not going to explain due to the time limitations. And about this supernova 1987A, by combining all these theories and observations at different points, astronomers have actually constructed the life story of that particular star, which became a supernova, right? So this will give you a good idea about this whole stellar evolutionary process. So that's why I have it here. Now for this, the star that led to this supernova explosion. So the estimate of the astronomers is that its central temperature initially would be this much, 4 times 10 to the power 6, and the density is 5 grams per cubic centimeter initially when it fused hydrogen, right? So this is the phase where it was in the main sequence, and the time spent in the main sequence is 8 times 10 to the power 6 years, right? And then the next phase is the helium fusion. When it fused helium, the central temperature has increased 190 times 10 to the power 6 Kelvin, and density has increased enormously. Now it is 970 grams per cubic centimeter. The time spent in that phase is now smaller. You can see that. Right? Now for the carbon fusion, which is the next one, 870 times 10 to the power 6. And the central density is 170,000 grams per cubic centimeter, you can see that from here to here, how the density has increased, right? And this has taken just 2000 years that spent in this particular fusion. Like that, if you look at this particular table carefully, you can actually, this is like a summary of the whole stellar evolutionary process. The temperature keep increasing when you go through this evolutionary process to make these heavy elements until core collapse to become a supernova, and the density at the same time is increasing, right, to the downward direction. And what is actually decreasing is the time spent in each of these phases. So it keeps decreasing, and you can see that when it becomes a like oxygen and silicon fusion, it only spent on those phases 1 year and several days after that. And when the core collapsing happens, it's like a tenth of a second. That is very, very quick, right? And this is one of the very recent supernova observations, supernova 1014J. This image of the supernova 1014J located in Messier 82, which is one of the galaxies. And this is also called as the Cigar galaxy, right? And this is actually a Hubble Space Telescope image, and is superimposed on a mosaic image of the galaxy also taken with Hubble. And this is a type 1A supernova, right? So the explosion was produced by a type 1A supernova, which is theorized to be triggered in a binary system consisting of a white dwarf and another star, right? As we discussed before, type 1A supernovas occur with a white dwarf star and another star, and could be a second white dwarf star like our sun. And for the type 1A supernovas, when you have a type 1A supernova, you can measure the distance, right? So that is important. And the distance is approximately 11.5 million light years from Earth. And how we will measure the distances from this type 1A supernova, we will discuss about that very briefly in the section when we start about cosmological distance scales, right? And this is in fact the closest supernova of type 1A discovers in past few decades, right? This is an example. And then supernova in distant galaxies with modern telescopes and detectors, it is now possible to detect supernovas in distant galaxies. And we have now, detected thousands of these supernovas, and these are, most of them are like billions of light years away. Normally when you have a supernova, they become very bright that, the brightness is very kind of overcome the brightness of the whole galaxy as well. Both types of supernovas in fact have been seen. And on average, we estimate that the supernovas are estimated to occur approximately once every 40 years per galaxy, right? Right, so let me just finish this. So I have these few words about the supernova remnants. So that is the debris from supernova, what is remaining after the supernova explosion. And there is the Crab Nebula is a good example of a remnant of a crab from the Crab supernova that we talked before, which was happened like nearly 1,000 years ago, right? And here are some examples of these supernova remnants, and I have mentioned the details here so that you can read through. Right, so that is actually the story about death of high mass stars. And if anybody have any questions before I move into the next section, I would like to answer for those. So I will give you some time. Please feel free to ask if you have any questions regarding death of high mass stars. And in fact, the next section is about what happens to this remaining part after you have type 2 supernova, right? Remember that we have this type 2 supernova, but at the same time, there is a core that was remaining, right? With neutrons, right? Which will become, in fact, a neutron star. So we are going to talk about that in the next section. But before that, if anybody have a question, I would like to answer those.
Excuse me, sir. I do have one small question. That
Yes.
the above picture it shows. Is it crab nebula? Yeah, it's crab nebula, and we
Yes.
learned in the astronomy, the first lecture in astronomy, that something called stellar corps. And is it the same thing that we call for crab nebula or something else? So I just want.
Okay. You said that it's still a corpse, is it?
Yes, sir. In the very first lecture, we learned something called stellar corps, and the same picture was there, and the remain was called the Crab Nebula. Uh, but the topic was stellar corps. So
I mean the first lecture, you mean the lecture that we did on Monday, right?
no, sir. I'm talking about the very previous lecture that we did with the general students.
This is the lecture that we did before the new year, then, right? Is it?
No, sir, sorry.
No?
I'm talking about the astronomy first lecture that we did with the general students.
Okay, very first lecture.
Yes.
Okay, so okay, then I will check it and let you know, right? So I can't remember about this. And
Okay,
so I will check it and let you know about the very first lecture. So this is, I guess, long time, right? Yes,
okay.
thank you for reminder. I mean, the answer for your question is most probably this should be the same, but I will double check what I have written there and let you know, right? On the next
Okay,
week.
sir. I just want to know what is stellar corps. That I know that is Crab Nebula, and I thought that Crab Nebula and stellar corps are both the same, and I just want to clarify
Um,
it.
it 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 should be the same, but this name right here that I mentioned, I need to double check it just to make sure whether I referred to the same thing or it's a different thing, whether it's a specific different thing. So that's what I want to check there.
Okay,
So
sir.
I will probably let you know on the next as the first thing on the next day, right?
Okay, sir. Thank you, sir.
I mean, in general, it should be the same thing, but I need to check whether I have referred there a different thing or not in the lecture. Right. So anybody else have a question like that? Right. So one thing is make sure that you, if you have a question, like, feel free to ask about it, right, and make it clear, because these topics are connected to each other, and sometimes, we talk about the same thing at few different places. So make sure that you make it clear, ask and make it clear, so that I can even check and let you know if I cannot give you an answer straight away, right? And if not, let me quickly go into the next section, which is about neutron stars and gamma ray bursts. I probably won't be able to finish it all the way, but I will try to start and talk at least about neutron stars. So I hope now you should be able to see my presentation called PHY4124 neutron stars, pulsars, and gamma ray bursts, right? If you cannot see it, then please let me know, right? So I just need to make sure, because I'm using two screens here. So. Right, by the way, to start with, the picture that you see here is a satellite called Swift. And this was actually a satellite that has detectors on board gamma ray, X-ray, and ultraviolet detectors, right? So this is actually used to do some cutting-edge research about gamma ray, something called gamma ray burst, which was, a mystery for the world of astronomy. I mean, until very recent, and we will talk about this towards the end section of this lecture about the gamma ray burst. And then let me right now, if you remember the two types of supernova explosions that we talked, the first one was a carbon detonation supernova. That is a type 1 supernova. Actually, that was the second one that we talked. The entire stellar core will explode and leaving nothing behind, right? This is what has happened to this white dwarfs. When they exceed this Chandrasekhar limit, they will become, the whole core will explode and you will not have anything. However, for the first type that we talk, that is the core collapse supernova or type 2 supernova, they have a dense core behind. The dense core will remain after supernova explosion, right? So you have the core neutrons. So that's what happens. These are for the type 2 supernova, which happens for these massive stars. And this is a very tiny core, and this tiny core consists of highly compressed neutrons. And if you remember that we talked about this in the last series of presentations, so you have very highly compressed neutrons at the end, and that is what remains after this type 2 supernova explosion, right, for the high mass stars. And this object with all these neutrons is what we call as neutron stars, right? Even though it is not undergoing fusion like an ordinary star, we used to tell that it's a neutron star. So all you have is compact neutrons, right? And you probably have heard about this word through the news when we have this detection about the gravitational waves, that they used to call that two neutron stars collide together and make gravitational waves, those kind of things, right? So this is how a neutron star is actually, created at the end, throughout, once you follow this stellar evolutionary process. As the end point of the high mass star, you will have either a neutron star or a black hole, right? So the first one that we are going to talk about is a neutron star. You will have the type 2 supernova, and the remaining will become a neutron star, which is densely packed neutrons. And these objects are actually very dense. Even you cannot think about the density of these things in our day-to-day life. And to give an example, so they are in the size of about 20 kilometers in diameters and more massive than the sun. And you can think about the size, right? The 20 kilometers means how long in our day-to-day distances. Just think about a sphere, a radius of 20 kilometers. Sorry, the diameter is 20 kilometers. That means the radius is 10 kilometers, right? This is, however, the mass of this 10 kilometer radius sphere will be equal to the mass of the sun. Now you can see that how dense is these objects are, right? Now this is why the normal physics theories sometimes doesn't work in this region. You can see that these are unusual objects, and this makes them billion times denser than white dwarfs and 10 trillion times denser than the Earth, right? You can see that how dense these objects are. And once we start talking about black holes, you will see that they are actually even denser than this. And this is why we need to talk about it under general theory of relativity, because different kind of physics works there, not the Newtonian physics, right? Here are some nice examples to show you the comparison between the white dwarf, which is the endpoint of a low mass star, and a neutron star, right? For example, mass is always, white dwarfs are, the mass of the white dwarf should be less than 1.4, because if the mass of the white dwarf exceed that 1.4 limit, it will become this type 1A supernova and completely explode, right? And for the neutron star, they are always greater than 1.4 solar mass and less than 3 solar mass, because the stars which are greater than 3 solar masses will become black holes, right? So that's what will happen, and we will talk about that in future. And the radius, you can see the size of the white dwarf is very large, 7,000 kilometers. Even though these neutron stars are very massive, they are actually just 10 kilometers in diameter, right? And in terms of the density, they are very large compared to white dwarf stars. So this is just a comparison for you about the properties of white dwarfs and neutron stars. Right. Now, these neutron stars will lead you to a different kind of objects that we call as pulsars. Right? As you know, the neutron stars are extremely small in astronomical scales, and they are very faint, right? Because you just have neutrons, right? So there is nothing for them to make them bright. There are no fusion reactions or nothing like that. And because of that, their existence has been predicted, but they were thought to be almost undetectable, right? So you should, in astronomy, to detect something, you should get some kind of electromagnetic waves from, right? I mean, straight away you cannot have, there is no way to detect those, even though we know that they are neutron stars. However, in 1967, there were astronomers using radio telescopes. So the telescopes that work in the radio wavelength, they have actually observed an object that was giving off rapid pulses of radio waves, which means you get a pulse of wave and then it goes away and then it comes again like that, right? And these pulses are very periodic, and they have actually measured the period. You get one pulse for every 1.337301 seconds. And these pulses are actually lasted for about 0.01 seconds and then goes away like that. And here is an example of pulses that they have detected, and you can see that for every time period, there is a pulse and then goes away, and then there is a pulse again like that. You have these pulses, right? And because of that, the astronomers used to call those new type of objects as pulsars, because they are giving off these pulses in radio wavelengths, right? And the interesting thing is, astronomers found a connection between neutron stars and pulsars, because they were looking for a way to detect these neutron stars, right? And at first, pulsars appeared to be found in blank places on the sky. What they have, when they searched for any objects, they did not see anything. They just saw these pulses, right? And but however, one was found right at the heart of the Crab Nebula. We know that pulsars are now neutron stars, right? And if you remember, when we talk about this Crab Nebula was a result of supernova explosion, right? So the idea is, once you have the supernova explosion, the remaining core should be there, which should become a neutron star, right? And so we can think that these pulsars should come from a neutron star, right? So that is the idea. And you can see that, so one thing that you have to learn here, apart from the astronomy, is that how people think in different ways to figure out things, right, in science, right? So that is something interesting, because you have the Crab Nebula, which is as a result of type 2 supernova. And once you have the type 2 supernova, you know that there should be a dense core consists of neutrons around that region, which should be a neutron star. Now, if a pulsar is coming from that region, you can assume that probably these pulsars may come from neutron stars. What we know now is neutron stars have very strong magnetic fields, which can accelerate charged particles. Now, you know that from your A-level physics that if you put a charged particle in a magnetic field, what kind of motion it has, right? Charged particles will be accelerated in magnetic fields, right? So the same thing happens in neutron stars. So they have strong magnetic fields which can accelerate charged particles. And as a result of that, there is an emission of radio radiation, right? And at the same time, these neutron stars rotate very rapidly. And this rotation is a consequence of, again, the angular momentum, right? And as the original star collapse, you know that what this means is a neutron star is become very dense and very compressed, packed very compressed, right? That means they become smaller and smaller, which means their moment of inertia is become smaller, and that will lead to the increase in the rotation speed. So this is why the neutron stars rotate rapidly. And this is, as you know, a conservation of angular momentum, right? So all of you should know about that. However, so you have, for the neutron stars, they have magnetic poles which are not aligned with the rotation axis, right? So neutron stars rotate, its magnetic poles may point towards us sometimes. And probably this may be clear from one of these models right here. And here is a nice model to look at that. You can see that here are the magnetic fields of from the red color. What you see is the magnetic fields of neutron stars, and here is the rotation axis. So the neutron star rotates around this axis, and it has a magnetic axis towards this direction, right? And because of that, they will emit these pulses towards this direction and this direction. So this is a model of a neutron star that emit pulses, right? And because of that, assume that we are right here on the Earth. So when this rotates like this, there will be a time these pulses will go through us, right? So we will detect a pulsar, and then when it comes to the other end, we will detect the same pulsar again, like that. This is how a neutron star can be detected as a pulsar, right? So just try to understand this model right here, which is very clearly explains what happens and how this neutron star and pulsar is connected to each other, right? Now the question is, now we know that pulsar is a neutron star. If we detect a pulsar, you can decide straight away that there should be a neutron star in that region. But whether the converse is true or not is a question, whether all neutron stars are pulsars, right? Now, the model of a rapidly rotating neutron star can explain the pulsar phenomena. For a given neutron star, we will not detect it as a pulsar unless its magnetic poles happen to point towards us during its rotation, right? Now, this is simple. If we go back here, think that its magnetic field is directed somewhere in this direction, right? So then what happens is, we will not be, even though there is a neutron star and it emits pulses, we are not in that path, right? We are right here. This is angled to a different direction. So in that case, there is a neutron star, but you will not detect pulsars, right? So that is what you have to understand. And that is what I have mentioned here. For a given neutron star, we will not detect it as a pulsar unless its magnetic poles happens to point towards us during its rotation, right? And so therefore, all pulsars are thought to be neutron stars. The converse is not true. So what that means is, if you detect a pulsar, it confirms that there is a neutron star in that particular location. But that does not mean that we have detected all the pulsars, because so that does not mean that we have detected all the neutron stars, because there may be neutron stars that detect, that have pulses that goes into different directions, and we cannot detect those, right? And there are neutron stars like that. And apart from that, this pulsar phenomena actually dies off after a few tens of millions of years, right? And this is due to the natural slowing down of neutron star rotation. When this rotational speed slows down with the time, and also its magnetic field weakens with the time, so there may be this pulsar phenomena goes away, and there are neutron stars in this kind as well, right? So that is important to know. So the take-home message is that there is a connection between neutron stars and pulsars. Of course, if you detect a pulsar, that means there is a neutron star. So they are connected to each other. However, the converse is not true. There may be neutron stars that you do not detect those as pulsars, right? So you have to remember that. And because of that, there are other ways of detecting neutron stars now. The radio pulsar phenomena provides the simplest method. But this pulsar phenomena sometimes seen at other wavelengths like visible light as well. And there are some actual neutron stars that are detected from the Hubble Space Telescope as well. And here is an example of a pulsar that is detected in other wavelengths. And this is, by the way, the Crab Nebula shows in X-ray emission. You can just read through. I have had a caption for each of these pictures that I put, which is actually copied from the book in the OpenStax. And if you go through that book, you have all these details there as well. And the caption, I have copied directly caption here, so that when you read it, you can get the complete idea, right? Even though if I do not have time to explain it, right? Now, here is another thing that I have mentioned here. Over the time, what happens is this pulsar slows down. So which means the period after 10,000 years, the period is 11 times per second, which means it has slowed down compared to when it was young. When it was 1,000 years old, you have 30 times per second pulsar, but it has slowed down after some time. Now the question is, where did this energy go, right? When it slows down, which means we have taken out some of the energy, and this energy is actually going to ignite or go on to this Crab Nebula if it is on the Crab Nebula, right? So what happens is the rotational energy is used to excite the Crab Nebula year after year, right? You can see that in these two images, the Crab Nebula get energetic from this lost energy from the neutron, rotation energy from the neutron star, right? Once again, it's the energy conservation that we talked in physics. Right, so I just need to finish up here. And on the next day, I will talk about the gamma ray burst, which will be on next Monday morning. And yes, so we will talk about a little bit about gamma ray burst, and then the stellar motion and binary stars on the next day, right? So hopefully, I guess I should be able to finish up the sections about the stars within next week and start about the galaxies. Now, anybody else have any questions up to here?